So we've been looking at stability, and we determined that if we have a single pole op-amp, such as a fully differential op-amp, or an op-amp where the two poles are separated by a large margin, such as a folded Cascode op-amp, then we don't have to worry about stability. But if we have a multiple pole op-amp and we use it in feedback, then the op-amp in feedback has the same poles as the open loop op-amp does. So we can say when our open loop response, little a of s, has multiple poles, our closed loop response, big A of s, has the same poles. For instance, we could write big A of s is equal to, approximately equal to, the DC closed loop gain divided by 1 minus s over omega p1 times 1 plus the DC loop gain times 1 minus s over some second pole, omega p2, times 1 minus s over omega p3. And we could keep adding poles. But what we're assuming here is that omega p1 is much, much less than omega p2 or omega p3. We began looking at this in class the other day, but we can define a specification that will tell us something about stability called phase margin. And phase margin is defined as the difference between 180 degrees and the angle of our loop gain at omega when the magnitude of the loop gain is equal to 1 or in dB, 0 dB. Now we want a phase margin greater than 0 degrees for stability. But we learned that if the phase margin is too small, that even though the system is stable, we can get ringing in the response, which also is undesirable. It means that we have to wait a long time for the system to settle. So generally, if we want fast settling, we want a phase margin to be greater than 45 degrees. And this gives us faster settling, better overall response. We can also define a specification called gain margin. And the gain margin for our amplifier is a similar thing to the phase margin. Our gain margin, GM, is equal to 20 log 10 of the magnitude of the transfer function, of the loop gain, at a frequency omega where the angle of the loop gain is equal to minus 180 degrees. And I say minus 180, but remember the phase can wrap up to plus 180 at the same frequency, so we should say plus or minus 180. Now in general, we want the gain margin to be less than 0 dB for stability. What we're saying here is that when the angle of our loop gain reaches 180 degrees, we want to have no gain left. And if we have no gain left, then our system can't have positive feedback. Now we can look at a few plots of what happens in a system with various degrees of phase margin. So we might look at a plot for phase margin equals 90 degrees. We can look at one for phase margin equals 60 degrees. And we can look at one for phase margin equals 30 degrees. And what we'll do is, these are plots are versus time. And what we'll do is we'll input a step into the system. At some time, they will index as time 0. So we input a step in. And what we would see if we had a phase margin of 90 degrees is that the system would be over-damped. So we'd have a long exponential settling time. So just like ringing, this is not desired. We don't want it because it's too slow to get to what we want. Now, if we have a phase margin of 60 degrees, we have a faster exponential settling time. And I'm exaggerating these curves, but the bottom line is this is a fast exponential settling time. Now, if we go down to 30 degrees, our system will rise really, really quickly, but it'll overshoot several times, and it'll take a minute to settle into the final output value. So there's ringing in the system, and so this takes too long to settle. So what we want is a phase margin greater than 45 degrees, and 60 degrees is what we would call critically damped. So looking at our definitions from control systems, our 30 degrees would be underdamped. "60" is critically damped. And 90 is overdamped. Now we can actually show that that if we have a phase margin of 45 degrees, we get the best settling time. So if we put a step in for a 45-degree system, our system is a little bit underdamped, but the output only overshoots once, undershoots once, and then settles into the output. So 45 degrees gives us fastest settling. Even though it overshoots, it still settles faster than the 60-degree case. Okay, so we'll start looking at actual op amps in the next part of the lecture.